Dear students, welcome back to the course Design of Power Electronic Converter. We are in the first unit, Analysis of Power Electronic Converters, out of which we have completed the design of buck converter. We have seen the various parameters and how to select various parameters and components ratings of buck converter. So today we are going to study about or try to solve the numericals related to the design of buck converter. So I would like you to encourage to take a notebook so that you can solve this numerical along with me. It will be easy for you to understand. Let's move on to the question. We have to design a DC to DC buck converter. So the specifications are given. A 100-volt DC power supply is connected to a load requiring 75 volts. So supply voltage is 100 volt and our requirement is 75 volt. And 900 watt. The power rating is 900 watt. Design a buck converter with the following specification. So input voltage is 100 volt, output voltage is 75 volt, output power is 900 watts, peak to peak inductor current ripple should be limited to 10% of the output current. Peak to peak output voltage ripple is limited to 2% of the output voltage, and switching frequency is 50 Hz. So these are the parameters, design parameters. We have to design our DC to DC buck converter for this particular specification. So these are the questions we have to solve. First, determine the duty cycle, determine the load current and average inductor current, inductor current ripple, inductor value, capacitor value. So inductor value in farad and capacitor in Henry, MOSFET voltage and current ratings, diode voltage and current ratings. So once you complete this, you have to draw the circuit diagram of the buck converter showing all the results. So when you are solving this numerical, you have to assume that the components are ideal and the converter operates in continuous conduction mode. So we have to design a DC to DC buck converter which is having input voltage 100 volt and output voltage 75 volt, which is working in continuous conduction mode. You can refer my previous videos for getting the formulas for solving this design. So you kindly pause this video and try to solve this numerical by your own. I hope you have tried to solve this numerical by your own, and let's see how we will get the results. So these are the given values. Input voltage Vs is 100 volt, output voltage 75 volt, output power P0 is equal to 900 watts, peak to peak inductor current ripple 10% of I0, peak to peak output voltage ripple is 2% of V0, and switching frequency Fs is 50 kilohertz. So what is our first question? First question is to solve the duty cycle. So this is a buck converter. So since this is a buck converter, the expression for the output voltage V0 of this buck converter is V0 is equal to D into Vs. This we have already learned in our power electronics. Also we have discussed in previous lectures. So output voltage V0 is equal to D into Vs. So we have to find what is the duty cycle. Duty cycle can be written as V0 upon Vs. What is our V0? V0 is 75 volt and Vs input voltage is 100 volt. So 75 upon 100 is 0.75. So duty cycle, if you represent it is in percentage, duty cycle is 75 percentage. Okay, now we can calculate the switching time period also additionally. We know that time period is the reciprocal of your frequency. What is the frequency given? Frequency given is 50 kilohertz. So time period is 1 upon 50 into 10 raised to 3. That is equal to 20 microseconds. This is the time period. And from this, we can calculate the on time and off time, T on and T off. What is your on time? D into TS. What is the 0.75 into 20 microseconds? We are getting 15 microseconds. So this is the on interval, turn on interval, and T off interval is 1 minus D into TS. 1 minus D into TS. What is 1 minus D? 0.75 into 20, that is 5 microseconds. So these are the additional answers. First question is actually to find the duty cycle. So we got the duty cycle as 0.75 or 75%. From that, we can calculate the T on and T off, which is 15 microseconds and 5 microseconds. Now we will move on to the second part of the question. You have to calculate load current and average inductor current. So load current is current flowing through this resistor, load resistor. Okay, so power is given. Power is 900 volt. This is a resistive load. So we can calculate the current flowing through the resistance by using Ohm's law. By using Ohm's law and power formula for calculating the power. Means resistance is not given, so we can't directly use the Ohm's law. I naught is equal to P naught upon V naught. Power is 900 watt upon V naught. Voltage across the load is 75 volt. So 900 upon 75, this is the answer is 12 ampere. So 12 ampere is the current flowing through the load resistor. Now, in continuous conduction mode, it is already given in the question that this buck converter is continuous, operating in continuous conduction mode. So, average current, this is your average inductor current, is equal to the average load current. Okay, so since we have calculated the load current, the same value is your average inductor current. So average inductor current is same 12 ampere. Now you can calculate the load resistance. Load resistance R is equal to V naught upon I naught. 75 upon 12, that is equal to 6.25 ohms. This is the load resistance. So here this part of the question is to calculate the load current and average inductor current. First calculate the load current, and the same value load current is equal to the average inductor current. So both are 12 ampere, and from that we can calculate the load resistance as well. Now next part of the question is inductor current ripple. You have to calculate the ripple. A ripple means the difference between the maximum peak and minimum peak current. Okay, the inductor current is not a straight line. It is a increasing. It is inductor is charging, discharging, charging, discharging. Let me draw that first. See, inductor current is like this. This is your inductor current. Okay, so this is the maximum point and this is the minimum point of inductor current. So delta IL is this difference between maximum peak current and minimum peak current. So this is your delta IL. Okay, so we have to calculate this. So for calculating that, what is given in the question? Ripple is given 10% of I naught. So we have already calculated I naught in the previous question. I naught is nothing but 12 ampere. So what is 10% of 12 ampere? 0.1, 0.1 or 10 by 100 into 12. 10 by 100 into 12 will give you the ripple current. So on solving that, you will get 1.2 ampere. So this is your ripple current. So here this is your average inductor. This is your actual inductor current, and average inductor current is average of this value. So this we have already calculated. This is your 12 ampere. This is 12. This is your average inductor current and this is your actual inductor current with ripples. So how can we find the maximum point and the minimum point? Average inductor current is 12 ampere. So and ripple is delta IL is 1.2 ampere. So average is in the middle of this inductor current. So how we can calculate the maximum point? Maximum point of this inductor current is this IL 12 ampere plus delta IL by 2. And what is this minimum point? Minimum point is total average inductor current 12 ampere plus minus delta IL by 2. So when you are adding and subtracting delta IL by 2, you will get the minimum point and maximum point of inductor current. So peak to peak inductor current ripple value is 1.2 ampere. So from which we can calculate this minimum point and maximum peak point of this inductor current. So here IL max is equal to, which is the maximum point, is average IL plus delta IL by 2, that is 12 plus 1.2 divided by 2. So on solving that you will get 12.6 ampere and IL minimum is this lowest point is IL average minus delta IL by 2, that is 12 minus delta IL is 1.2 divided by 2, that is 11.4 ampere. So peak to peak current is 1.2 ampere, IL max is 12.6 ampere, IL minimum is 11.4 ampere. You try to solve this numerical along with me. Now you have to calculate the value of inductor. Value of inductor. So it is represented in Henry. Okay. So how we can calculate the value of inductor? When the MOSFET is in on condition, so this we have discussed in previous lecture. VL, voltage across the inductor is Vs minus V0. Input voltage minus output voltage. Okay, and using VL is equal to L delta IL by T1, we get this we have already derived in the previous lecture. L is equal to Vs minus V0 into T1 divided by delta IL, or T1 can be represented by D by Fs. T1 is D divided by Fs. So on substituting, we have all these values. What is Vs? Vs is the input voltage, which is 100 volt. V0 is the output voltage, that is 75 volt. D is 0.75, or we have already calculated T on. You can directly use T on, or you can use this formula. D is 0.75 divided by, what is Fs? Fs is 5 into 10 raised to 3. 50 into 10 raised to 3, 50 kilohertz into delta IL we have calculated here 1.2 amperes. So on solving this, you will get 3.124 into 10 raised to minus 4 Henry, or this can be written as 312.5 microhenry. So this is the value of inductor that you have to use in this circuit for getting the 75 volt as the output voltage. Now we will design the capacitor value. Capacitor value is, we know that the maximum peak to peak output voltage is 2% of V0. So what is your V0? V0 is 75 volt. So how much is 2% of V0? 2 by 100 into 75. So 0.02 into 75. So 1.5 volt is the peak to peak. This is the ripple value. And for a buck converter, this delta V naught, expression for the delta V naught is delta IL divided by 8 Fs into C. This formula also we have derived in previous lectures. So from this formula we can write C is equal to delta IL divided by 8 Fs delta V naught. So substitute all the values. Delta IL is 1.2, which we have derived in previous part of this numerical, 8 into 50 into 10 raised to 3 into delta V naught is 1.5. 1.5. So substituting all this, we will get 2 into 10 raised to minus 6 farad or 2 microfarad. Okay, so standard capacitor value 2 microfarad capacitor is not there, so we can use a 2.2 microfarad capacitor for this voltage rating, getting the particular voltage rating. Now we have to calculate what is the MOSFET voltage and current. MOSFET voltage rating. MOSFET voltage is your capacitor voltage across the capacitor or voltage across so what is the actual voltage, because when you select a device we should consider the maximum of voltage, and your MOSFET should be capable of handling that maximum voltage. So here if your voltage, if suppose your capacitor voltage is like this is the maximum point. Okay, so your MOSFET voltage rating should be greater than this value of voltage. We should not consider the average voltage, because if the rating, all the ratings of the devices we are using in the converter should be above the maximum rating. Otherwise, if the voltage is exceeding, your MOSFET will get damaged. So how you can find the MOSFET rating? The MOSFET rating can be calculated by calculating the peak value. What is the peak value? Vs plus delta V naught by 2. What is your Vs? Supply voltage is 100 volt and delta V naught is 1.5 divided by 2. So this is the peak value, 100.75. So the rating, voltage rating of the MOSFET that you are selecting for this particular buck converter should be above 100.75. So when you look in the data sheet, you can understand that what is the MOSFET rating, and when you select particular MOSFET, you have to make sure that the voltage is above 100.75 volt, because there is a chance for voltage to go beyond voltage can go up to 100.75 volt. Now we will see the current rating. In the same way, for current rating also, the MOSFET current should be higher than your load current, maximum value of load current. What is the maximum value of load current? I naught plus delta IL by 2. This is the peak value. Okay, so the rating of the MOSFET, current rating of the MOSFET should be greater than this maximum value. 12 plus 1.2 divided by 2 will give you 12.6 ampere. So your MOSFET current rating should be above 12.6 amperes. So here when you are practically taking, we always use an extra margin. So when you are taking the selecting the MOSFET, we can select a MOSFET with 150 volt and 20 ampere current rating. I hope it is clear for you. Now we will move on to the last part of the converter design, diode voltage and current rating. We have a freewheeling diode in the circuit and we have to find the voltage rating of the diode. And diode rating is also same as that of the MOSFET rating. The voltage should be greater than the supply voltage, because when the switch is in on condition, the voltage across this diode is directly the supply voltage. So we have to consider that supply voltage Vs plus delta V naught by 2, that is Vs is 100 volt, delta V naught is 1.5 divided by 200.75. So the diode voltage, reverse voltage rating should be 100.75 volt, above 100.75 volt, and the current rating of the diode is greater than your load current, peak value of load current. So what is the peak value of load current? I naught plus delta IL by 2, that is 12 plus 1.2 divided by 2, that is 12.6. So here when you select the diode, the rating should be greater than or equal to 150 volt and the current rating is must be 15 to 20 ampere. Okay, so here we can draw the buck converter with all the ratings what we have discussed till now. So buck converter supply voltage is must be 100 volt, output voltage is 75 volt, Resistor value is 6.25 ohm, capacitor value is 2 microfarad, inductor value is 0.3125 millihenry, and your diode voltage must be greater than 100.75 and current rating must be greater than 12.6. In the same way, your MOSFET rating also should be greater than 100.75 voltage rating, and your current rating should be greater than 12.6 amps. So in this way, you can design a buck converter for your particular applications. Like say for example, if you're designing a DC to DC converter for an EV or whatever project you are doing, if you are knowing the supply voltage, and if you know what is the output voltage requirement and the switching frequency, with these three values we are able to design a buck converter with all these ratings. Okay, so this is the summary of all the rating. Capacitor value C is equal to 2 microfarad, MOSFET voltage greater than 10.75, MOSFET current rating greater than 12.6, diode reverse voltage rating greater than 100.75, diode current rating greater than 12.6. So when you're actually designing, so these are the practical value. We need to keep some margin. It should not be less than this value. It should be always greater than what is the calculated value. So in this way, we are able to design a buck converter. Thank you so much. Try to solve this numerical by yourself. I'll give you few more numericals which is in similar way you can solve this. Okay, thank you for listening.